Thanks for coming today. I'm Randy Holland, Marketing Director and Product Specialist for Safety Cover Enclosures. I have a presentation today that I think you'll find important, not only because it relates to wholesale changes in the way designers approach the water supply aspect of a site, but also because I bring specific information about changing dispositions among water purveyors in Illinois. Today we'll cover ordinance changes that affect you as a designer. This report covers the 15 most populous cities in northern Illinois. We refer to it in our office as the Chicago Watch List. I have specific change information about Chicago, Naperville, and Elgin. Not only are the details important in and of themselves, but they foretell with some clarity just what's happening among water purveyors across the country. Given these new realizations, we'll look at design considerations that are implicitly demanded of you. But first, cross-connection control, Backflow 101, a quick overview of cross-connection control, what backflow is, why it's bad, and what the waterworks industry has devised in the effort to neutralize its risk. So, why do we need a cross-connection control program at all? Well, that's easy. Safe drinking water. But how does backflow prevention protect drinking water? I think this ancient art illustrates the point perfectly. Our friend has attached a pressurized sprayer to his garden hose spigot. Because the pressure in that sprayer has now overcome the ambient pressure in his home's water line, some of that sprayer's chemicals are now flowing back into the city's water supply at the street. At the same time, his neighbor draws a glass of water from her tap, giving new meaning to the word firewater. Okay, the funniest thing about this picture isn't anything I've said yet. It's actually the dog. I don't think the illustrator intended it, but there's got to be either fertilizer or weed killer in that pressurized sprayer. And he's offering this dog a ball that's been rolling around in that grass. I have a theory. Maybe this guy hates his neighbor and this is actually her dog. It could be he's hoping they'll both get the proverbial dirt nap tonight. Backflow happens when either or both of two events occur. The example shown here and in the previous illustration is backpressure. It happens when there is a higher pressure existing in the downstream piping than in the supply piping, allowing downstream substances to be pushed back into the potable water supply. Pumps, thermal expansion, elevation, these are among the most common causes. The other event that causes backflow is back siphon. Back siphon happens when there is a negative pressure in the supply piping, allowing downstream substances to reverse direction and be pulled back into the potable water supply. Typical causes are water main breaks, or even higher than usual withdrawal rates, such as a flowing fire hydrant. You, as a designer, may specify one of two types of backflow preventer generally, the double check valve assembly or the reduced pressure zone valve assembly. As the subtext indicates, the difference between the two devices is perceived hazard. But how do you determine hazard? Well, that's a good question. And the simple answer is that the purveyor determines it, but most every jurisdiction is different. Every city has its own list of named examples of what constitutes the hazard threshold. But they all stipulate that if the anticipated use as you know it is not named explicitly, then they reserve the right to make the decision during code's review. It's important to understand that you cannot, as a designer, overprotect the incoming water service, meaning there is no penalty for providing the higher degree of protection. So you should ask yourself, is there wisdom at all of providing the lower level of risk protection? So let's have a quick look at how these things work. The double check assembly was developed in the 50s, and for what it does well. Anytime pressure on the downstream side exceeds pressure on the supply or public side, the valves close and the water stops flowing backwards. Keep in mind that no remedy exists in the event of a malfunction of the valve closure or if debris in the line causes the valves to not close completely. Before we move on to the RP, I want to just cover the detector assembly. The detector assembly can apply to either one of the backflow preventers we're talking about today, either the double check or the RPZ. The difference in the detector assembly is it essentially consists of a bypass assembly that piggybacks the primary backflow preventer with a meter in order to detect any unauthorized use of water and or leaks on the system. Now, mind you, it doesn't provide an accurate measure of water flow since it's such a smaller diameter device. And here's, by the way, as it exists in reality. You can see that it's a much smaller set of pipes that come across that double check assembly, and the meter piggybacks right over the top of it. The purpose is not to measure the flow, but to simply indicate flow and to detect leaks. The reduced pressure zone assembly consists of two independently operating check valves, just like the double check, plus a hydraulically operated differential relief valve located below the first check valve. Static or no flow condition, both check valves are closed. Pressure on the supply side of the valve is about 8 psi higher than the pressure in the reduced pressure zone side, so the relief valve remains in the closed position. When water flows from the supply side, both check valves open. The hydraulic relief valve is also held in the closed position, again because the pressure on the supply side remains higher than that of the reduced pressure zone side. This illustration shows how the RPZ protects the water supply in all situations. It's really quite elegant, but it does come at a cost to the area around the device. When a negative supply pressure occurs, both of the check valves are closed. At that moment, the relief valve will open every time and evacuate all the water between the valves. Well, some think that that event defines the limit of what water can ever flow into a drain, but that's just not so. If you look closely, you can see that a small pebble has lodged in the number 2 check valve. Because the number 2 check valve is not closing, water will continue to flow out of the relief valve until the private lines are cleared. Now, if this is a 4-story building, that's a lot of water. Now, consider a full failure of the number 2 check valve. Now you have water flowing through the relief valve at head pressure. Again, if this is a large or multi-story building, that's a lot of water very fast. Finally, consider a failure of both check valves. In that event, water will flow at a pressure higher than the supplied pressure because you have to add the head pressure to the supplied pressure. And this water will flow until those valves are manually closed. This picture was tweeted this summer by a Nashville backflow tester. It reads, "This is why we do it. A tiny pebble can render them useless. We test them right." There are basically 3 options for backflow preventer placement, and all 3 are widely practiced. First, inside a vault. This would have to be considered the legacy method still widely practiced among designers today, but as most of you know, an RPZ can never be installed below grade. So, as purveyors are moving to higher levels of protection, the vault is losing favor. But as it remains for lower hazards, let's look at the considerations. We've identified 3 issues with vaults. They are safety, liability, and changing demands. We've all seen the extraordinary measures OSHA imposes to legally access vaults for maintenance tasks. Fresh air exchange hoses, tents, extra men. The costs are more and more prohibitive, but frankly, the risk of serious injury is real as well. But beyond the cost of safety for on-site workers, liability issues persist. When a vault floods like this one, the mandatory test cocks are submerged, and in that event, a violation of the International Plumbing Code has actually already occurred. The water may look clean, but consider what would typically make up the constituents of that water. Runoff of lawn chemicals alone make this a clear and present danger to the water supply. In fact, it led the USC Foundation for Cross-Connection and High Research in 2005 to change their recommendation of even double-check backflow preventer installations in vaults. They said the Foundation's recommendation would be to install the double-check valve above grade. Finally, changing demands. As we consider exemplary designs, remember that buildings, through their normal life of changing tenants over time, change uses with respect to hazard levels. And hazard levels, in and of themselves, have become a moving target. Around the corner from our office in Nashville, I snapped this picture. It sits in front of a warehouse owned by an automotive dealer. When they bought the property and erected the building, they put a double-check backflow preventer down in that vault with the meter. A few years later, the city decided they needed to install an RPZ instead. After constructing this huge vault, they now leave it almost empty, with an RPZ in an enclosure perched on top of it. Because they built this enormous vault, they paid easily 3 times what they needed to pay for a single solution. What about inside a building? If the double check valve is commonly deployed to a vault, then equally common is that the RPZ is deployed to an indoor location. Let's look at the concerns for the designer. Accessibility can certainly be an issue, but more and more, ample room for testing and maintenance is being allocated. It's certainly appropriate to list it as a concern, but that's no longer the big issue. The main concern is property damage liability due to flooding. Here's what the American Society of Plumbing Engineers published in their 2006 design handbook. Before an RPZ is located, consideration should be given to both how much water will be discharged and where it will drain. Consideration must be given to the drain system to assure the drainage system can handle the load. If a drain is not capable of accepting the flow, other choices as to the location of the valve, such as outside in a heated enclosure, should be made. As we've illustrated then, an RPZ behaving as designed dumps water. This flood occurred in a hospital mechanical room and caused over $1 million in damage. You're looking at 2 sides of one wall. On the left, we see that the sudden water volume moved the wall into the next room, which happened to be a telephone and low voltage wiring room. Of course, the insurer sought recovery from all the risk holders, including the engineer, the architect, the contractor, subcontractor, and even the most recent recorded tester. And while the details of who paid what were not made public, we do know that the property insurer was made whole by one or more of those listed defendants. So if these things are designed to dump water, then drain capacity is the real issue, right? The chart on the left is from Wilkins Corporation. It's the relief valve discharge rate chart for its top-of-the-line RPZ, the Model 375. It illustrates the flow rate of that device at various sizes and at various pressures. Note that a 2.5-inch device will flow 375 gallons per minute at 85 psi. If you remember your fluid volume tables, and I'm sure you all do, you'll recall that a 4-inch drain pipe with a 6-inch fall per 100 horizontal feet evacuates clean water at a rate of 93 gallons per minute. If that device is flowing at 375 gallons per minute and you're only clearing 93, then you're flooding at a rate of 282 gallons per minute. An article published this summer in the Chicago chapter of the American Society of Plumbing Engineers, written by David DeBoard, a former president of that organization, states all these facts much better than I can. He uses the manufacturer's data supplied by the Watts Corporation instead of the Wilkins Corporation, as I did, and he uses 65 psi instead of my 85, but he actually does the math in the article and offers what he calls flood rates of 219 gallons per minute for the 2.5-inch models and a flood rate of 482 gallons per minute for 4 inches and above. He concludes that regarding indoor RPZs, the floor drain capacity of RPZs of 3-inch diameter and higher are likely to be cost prohibitive due to the necessary pipe diameter and fall rates. The last place you can specify a backflow preventer is above ground in an enclosure. Let's take a look at the considerations. Freeze protection, strength, drainage capacity, accessibility, and security. In 1996, the American Society of Sanitary Engineers developed a safety and quality standard for above ground enclosures. It's known as ASSE 1060, and it addresses all 5 of these concerns. Freeze protection to 30 below, vertical load strength of 100 pounds per square foot, full flow drainage capacity, and with respect to accessibility, we sought and obtained from OSHA this written confirmation that our enclosures do not qualify as confined space hazards, subject to its many safety constraints. Within a few years, the IPC adopted the new standard, and that code simply reads, outdoor enclosures for backflow prevention devices shall comply with ASSE 1060. So given our earlier fascination with the topic of liability, we add that parameter as an additional consideration here. Doug Krieger is an attorney that specializes in cross-connection control litigation and advocacy. He was quoted in Plumbing Standards magazine initially in 2009, and then it was rerun just last year. He said an outdoor above-ground backflow preventer installation may be the best way to, 1, reduce the owner's exposure to damage caused by flooding and the corresponding water contamination caused by a cross-connection, and 2, reduce the legal liability of the design engineers, the installers, and the certified testers whose professional actions in part may have otherwise caused the flooding harm. The water industry has a nationally accepted design criteria in ASSE's 1060 to protect these installations. It's a win-win-win insurance policy. Allow me to offer Exhibit A in this more enlightened approach. Roswell, Georgia is an Atlanta suburb of 200,000 people in Fulton County. Because legacy methods die slowly, they've articulated a very sensible middle ground position for getting more backflow preventers out of harm's way. They've detailed 2 methods of RPZ placement, one indoors and one outdoors, explicitly addressing the drain pipe requirements for all equipment with those previous shown tables. Placing these tables in the indoor installation standard forces designers to reconcile the flood rate risks with drain capacities, and the outdoor method mandates an enclosure that is ASSE 1060 compliant. These kinds of standards are appearing all over the country. Here are some examples. Northern Illinois seems to be getting on the train. It all started last fall with Elgin. On October 24th, they amended their domestic water service requirements as follows. In all new commercial and industrial construction, each domestic water service shall have a reduced pressure principal backflow preventer assembly installed directly after the city water meter. And then they repeated that verbiage to include all remodels as well. A few weeks later, Chicago changed their backflow placement requirements as follows. All new combination fire and domestic service shall require a domestic meter and an approved backflow device with bypass meter of the fire system. If these services are in excess of 50 feet for 2 inches or 100 feet for 3 inches, they must meet the above requirement and shall require the backflow preventer to be installed in an above-ground heated enclosure located as close to the property line as physically possible. Finally, just after the first of the year, Naperville saw Elgin and raised them one by calling for RPZs on all commercial and multifamily lines, irrigation, fire, and domestic. So why inside at all? Ever. There are issues with access for testing and maintenance. There are issues with property damage due to flooding, issues with changes of use over time, and there are issues with changes in a purveyor's requirements over time. I know why you don't like to do it. You're afraid we'll sell you something that looks like this, or this. This is our weed eater model, or my personal favorite. Folks, this is a situation where the purveyor changed their mind what they want to have in place. In the foreground there, you see a vault. Previously, they had put a double-check backflow preventer down in that vault, no doubt next to the meter. Later, the city changed their mind on what was required and asked them to move the device above ground and install an RPZ. Sadly, the enclosure they chose was not of sufficient height to allow full coverage those OS&Y valve shutoffs, so they just made holes for them. This is actually a fiberglass shower stall that they've decided to call an enclosure. We think these devices are the most beautiful things ever. Don't you agree? This is our Northern Illinois watch list, the 15 largest cities by population. The first 3 columns indicate where an RPZ is required for domestic fire and/or irrigation lines. Green means yes, yellow means it depends, and red means no, a double check is okay. The second 3 columns indicate whether an RPZ is allowed domestic fire and irrigation. And as we discussed, no districts Refuse the use of RPZs for any purpose where you deem it appropriate. Finally, the last column indicates whether it's acceptable for any and all types of backflow preventers to be installed in an outdoor heated enclosure, whether it's DC, DCDA, RPZ, or RPDA. And as you can see, all these jurisdictions do allow this. Consider this. You're designing multi-million-dollar systems that will remain in service for the rest of your lives and beyond. Not only are they multi-million-dollar projects, there are also millions of dollars of liability embedded in these projects. An 8-inch backflow preventer is a very large device, and yet the difference in cost is just $1,100. So why think twice about providing the highest level of protection? What's in it for you? Finally, I want to let you know about a great little tool. Click on our website. At the very top, there's a button that reads, "Click here to size your backflow preventer." There you'll see a simple 7-step calculator that allows you to specify the exact enclosure needed for your job. We'll isolate what we need here. We'll say an RP, that's 6 inches, let's say. I'll choose Wilkins, and they're 375. OS and Y is the shutoff. Yes, we'll use a strainer, and we need 12 inches of clearance. So I hit search, and because I've been so specific with my parameters, it will be equally specific with its selection. My project will require a model 600 AL. I click on that link to get all the specifications in PDF form. Return to the solution page, click View Backflow, and see the enclosure with the named backflow preventer inside in both an elevation view and a plan view. These are also in PDF format that I can drop right into my drawings. If you have any questions or comments, please email me at randy@safetycover.com or phone me at 800-245-6333. Thank you for your interest in safety cover enclosures. If you would like to be notified when webinars and other educational tools become available, please go to safetycover.com, select Design Support, then Continued Education. There you'll find a simple sign-up form for updates. Please bookmark this YouTube channel for more professional development hours and continuing education training for engineers.